Okay, let's get started with this new topic. Centroid of an area. That's what we are going to talk about this this session today. Well, the centroid of an area is basically the location of the weight of a body. How to find the location? Where do you put the weight of a body? We have been talking about center of gravity all the time. That's where the weight is applied, right? How to find that location? The basis behind how to find the location of the center of gravity is again based on another the topic that we have discussed several times, is that equivalent forces. When you have a force here, you know that you can move that force along the line of action. You can move that force like from this location to this location, and this force is equivalent to this force. Those two forces are equivalent. You can move a force along the line of action as long as you are talking about non-deformable bodies. Um, you can put this force anywhere you want along the line of action, and that's okay. The forces can slide through the line of action with no problem. But if you want to move that force out of the line of action, let's say you want to move it here, you cannot say that this force is equivalent to this force. That's not true. Because the idea that two forces are equivalent, or two systems of forces are equivalent, is based on two facts. It's based on the fact that the magnitude of the force or the system of forces has to be the same, which in this case it is. In this case, the magnitude is F, and in this case, the magnitude is F. But the moment that the system of forces produced with respect to a point has to be the same in both cases. So this force here, if you calculate the moment of this force with respect to any point, you will get an amount, whatever, and then this force has to produce the same moment, or this. So these two forces don't produce the same moment, because if say I calculate the moments with respect to point A here, this one doesn't produce any moment, but this one does. This produces a moment equals to force times distance. If this is the distance d, so there will be a moment here equals to force times d. That doesn't is not the moment that this one is producing to the same point A. So these two systems, this one right here and this one right here, is not the same. So in order for those systems to produce the same moment, you have to have another moment here that balance this one out and cancels that one out. So in that case, the first, let's call this one the first system, which is just one force, is equivalent to the second system, which is this force plus this moment here, Fd. So let me put it here. So I have the system F, this is the first system, and the second system, which is F plus a moment here equals to m times d. Well, this is d, right? Because system one, both have a magnitude of f, which is the first condition, so good for that condition. But now, if we calculate the moment of both systems with respect to point A, the moment here is equal to 0. And how about the moment here? The moment here is equal to, let's put positive in this direction. So we have the force times the distance produce F times D. And then this moment in the opposite direction minus F, sorry, this was F here. F times D equals to 0. So see how this system 2 is producing a moment of 0, and system 1 is producing also a moment of 0. So these moments are the same, and these magnitudes are the same. So these two systems are equivalent. So that's why every time you move a force outside of the line of action, you have to apply, if I want to move this force over there, I have to apply a moment here equals to F times D in order to have this system 1 equivalent to this system 2. These two systems are equivalent, so it's the same to have system 1 or to have system 2. And you can verify that if you calculate moments about any point in the universe, point C, point D, point H. If you calculate the moment of those two systems with respect to any of those, any point, you will get that the moment is the same no matter where you choose the point. Once the moment is the same for both systems with respect to a point, it will be the same for any point that you choose. So that's the concept behind how to find the location of a center of gravity. The idea is that any object is made out of all its particles, all the particles that make up the whole body. Each particle has its own weight. And if the particle has no dimension, it's just a point, you know that the center of gravity is right there because there is no other, is where the point is located. So if you base your analysis in that fact, then we have to find, let me draw it here. I have the picture on the left is a plate. Both are the same plate. The plate on the left is the plate which has already all the weight concentrated in one point, and that point is the location of the center of gravity, where the coordinates of that point are called y bar and x bar. And we need to find y bar and x bar. Is x bar. We need to find y bar and x bar, and in such a way that the moment, the magnitude of the magnitude of W has to be equal to the summation of all the magnitudes of all the little components of the body. That if I divide this plate in tiny particles, let's say this point here is one particle, let's call it delta W. So the weight of that particle is this tiny delta W. I know that the location of that delta W is known because it's right where the particle is. So this will be the location of, it will be Y, and this will be X. So the location of delta W is given by X and Y. So in one sense, I need that the total weight is equal to the summation of all the little weights. So the system that I have here on the left meets this condition. The magnitude of the force has to be the same. And the other condition is, let's calculate the moment of the big W with respect to the x-axis moment, or let's do first with respect to the y-axis. The moment of the big W, big weight, with respect to the y-axis is equal to the force times the distance. That moment has to be the same moment my produced by the summation of all the particles that make up the whole plate. So this will be, that has to be equal to every little weight multiplied by its own lever arm. In that case, this will be x. So if these two are equal, we meet the second condition. This is that the forces, the magnitude of the forces is the same, and the moment produced is the same. And we are going to do this for the other axis. The moment produced with respect to the x-axis is equal to W times y bar. So this has to be equal to the moment produced with respect to x by all the component particles, which is delta W times y. Okay? We have been talking all the time about the moment of a force with respect to a point. This is what we are doing here, moment of force with respect to a point. The thing is we are looking at this like in 3D, but if you look at it in 2D, like we have been looking at moments during the past lectures, if you look at this plate from this side, let's say that you have here your point of view. So you will see this will be your W, and this will be your y-axis. It will be the y-axis like a point, right? A point going into the paper, where this distance is x bar. You see it? So that's what I mean by moment of y equals to W times x bar, this equation. And we can do the same in the other directions, basically the same. So now, when we are calculating here W times x bar, we say is the moment of the force W with respect to point y, but point y is not a point; it's an axis that goes into the paper. And same thing here. What I'm doing here is that I have one of the particles that make up the whole plate is here. Is a tiny particle of weight delta W, and this is the point Y. It's not really a point, but an axis. It goes into the paper, and this is the distance X. So if you take all the points that make up all the plate, all the points that make up the plate, each one will be producing a tiny little moment. If you get the total moment, will be the summation of the moment of all those little weights multiplied by the lever arms X. So what we need in order to produce, to locate the center of gravity is meet this condition first, that the weight is the summation of all the little weights that make up the total plate, and that this moment y with respect to the axis is equal to the same moment that is produced by the components of the plate. So based on that fact is that we are going to find what is x bar and y bar. Summation of moments has to be the same. Summation of forces has to be the same. So the question that I'm going to use is this one. W times x bar is equal to summation of delta W times x. So x bar is going to be equal to summation of delta W times x divided by W. And same thing for y bar. Exactly the same thing. So y bar equals summation of delta W times y for W. Okay. So this is how to find the location of the center of gravity of a plate based on the fact that I know the location of the center of gravity of each delta W is kind of like tiny components. Let me calculate the weight of the plate in terms of the area. The weight is equal to the volume times the specific gravity, right? That's the weight. And the volume is the area times the thickness of the plate times the specific gravity will give you the weight, where the thickness of the plate will be this dimension here. Let's call it the thickness, T. So that will be the weight here. And the weight of one of the components delta W, same thing, will be the volume of the little piece multiplied by specific gravity. We should call this one delta volume because it's like a little volume. And that will be equals to delta area, the area of the tiny particle right there, multiplied by the thickness, multiplied by specific gravity, That will be delta W. So our equations will become these equations will become A T omega times X bar equals to summation of delta A T omega X. So we can do here T is constant for all the elements and the specific gravity for an homogeneous sheet or plate. So we will have that X bar is equal to summation of delta A times X divided by area. And in the same way, we could do the same for Y. Then we'll have summation of delta A times Y divided by A. All right? We're talking a very tiny components, but we have finite number of pieces of the element. Then we will have this expression F sub I X I over area and Y bar equals summation of X A sub I Y I divided by area. Or on the other hand,
I have a question. So the angle that you have there that looks like an R, right next to the A and the T.
Is
Yeah, that one. Where is it located in the graph?
this is the specific gravity, like equivalent to it's like the density. Think about the density, but it's actually density multiplied by G, by gravity.
Oh, okay. Is it a constant?
Yeah, it's like the material that makes up the plate. When you say weight is equal to mass times G,
yeah,
then you can say mass is volume times density times G. This is a specific gravity. It's kind of like the weight of the density.
Oh, okay, that makes sense. Thank you.
This is what this is. Yeah, this. And if we are talking here of a plate that is made of the same material, the whole plate is made of the same material. So the weight is the volume multiplied by this is what tells you what is the weight of every unit of volume. Multiplied by the total volume, you get the total weight. Okay. Okay, where were we? Okay, here. So now, so we have this expression, and then we can get another expression when you talk about infinite number of particles, which when you cannot divide say in this case the plate into a finite number of areas, but you have to go to the root of the components of the plate. You go to infinite number of particles, then the delta becomes the differential. So, and the summation becomes the integral. So you will have X bar equals integral of dA times X divided by area. Integral of dA times Y divided by area. So if we don't know the location, if we know the location, we have a plate and we can divide this plate into a finite number of pieces, and we know the location of each one of the pieces, we can use this equation here, these equations here. But if we don't know that, we have to go to the very basis, which is divide the big body, the big plate, into the smallest component part, which will be just an infinitely small particle. So you have to go to the integral. So let's suppose that we don't know where is the center of gravity of nothing. Just we know just that if you have a particle, you know that the center of gravity of the particle is right there in the particle, because it has to be right where the particle is located. So if we have a particle here, so if we have a particle here, a little dot, where is the weight of that dot? Well, right there. There is no other choice. I couldn't think of like if I have a dot here, or a tiny speck of matter, that the weight of that matter is here outside of the matter. That's not logic. So we know this fact that a dot has its weight right where the dot is located. So in that case, we have to go to the integral. So based on that fact, we could find the center of gravity of a thin strip. Say that we have, let's call it this example one. So yeah, well, let's call it example one. Center of gravity of a thin plate. We call this centroid of a thin strip. And let's do it only in the x direction. Let's do it only on the x direction. So we have here our x-axis, and we have a very thin strip where this, let's say this thickness is very small, and the strip has a length L. So we're going to divide this strip into infinitely little components of length dx. So those are infinitely small, and we can say for sure that if this is infinitely small, the center of gravity of that tiny thing is right here, and it's called dw because we are meaning very little, infinitely little. And the location of that little thing is, let's call it here x. So the moment that this little part of the body produces with respect to the origin here, which is actually in the other representation, this would be the x, y, and this will be the xz, sorry. So then we have that the moment produced by all the little dots that goes from 0 to L will be the integral of dw times x, right? That's what we have somewhere on the top. But then we came down by eliminating t and the specific gravity. We came down to the expression that I have right here, that x bar is equals to integral of dA times x divided by the total area. Yeah, let's don't start from the beginning. We already arrived to this equation. So that's how we can find the location of the center of gravity of a little strip, a very thin little strip of width t and length L. So we need to make this integral. So we need to find dA in order to find the integral. What is dA? dA, the area is equal to the base is the x and the height is t. That's the A, right? And the area is L times T. So our expression x bar will be equal to integral from 0 to L of dx times T divided by L times T. So T is constant, so can go out. T integral of dx is x. Oh, sorry. I am missing x, right? dA is dx times t. Here dx times t and x. So I have to put x. So this is t integral of x dx divided by lt. So we can cancel this, and this is from 0 to L. So we have x squared over 2 from 0 to L divided by L. So we have L squared over 2L, L over 2. It looks like a very simple finding. And we knew that, but we are kind of proving where did you find that the center of gravity of a little strip is right in the middle. So this is where you can locate the total weight of a strip, where if this is L, this is L over 2, and this is L over 2. Now we have proved that the center of gravity of a uniform material little strip is in the middle of the length. And look at this location, x bar equals L over 2, is independent from t. It's independent from t. So we can have any t and we should get the same result. So this we can extrapolate to a plate that is length L, and let's call this L B and this H. So the center of gravity is here at B over 2, no matter what the dimension H is. And if we move it 90 degrees like this, and we do the same calculation, now we have a strip that is very wide, where this is A, this is B, and this is our X direction. If this is A, so the location of the center of the centroid, this X bar, is equal to A over 2. Because in this case, this is the famous T. Now is B a very large dimension. It doesn't matter because the location of the centroid, it doesn't depend on this dimension. It only depends on this dimension. So now we know that for any rectangle, the center of gravity is in the middle of the dimensions of the rectangle, A over 2 and B over 2. That's something that we already knew, right? But we are proving it based on these basic conditions of equivalency of forces, how two systems of forces are equivalent. The magnitude of the forces has to be the same, and the moment produced by the systems of forces has to be the same. That's how you locate the center of the gravity of a, in this case, placed in 2D. And it's based for uniform plates. You can work it with areas, and this is the concept of centroid of areas. So now that we know where is the location, we know for sure, and we are certain that the location of a strip is in the middle of its length. We can find the centroid of a more complicated figure. Let's call it example 2. We're going to find the centroid or right triangle. So let's do our right triangle. Let's put here an axis y. Let's put here another axis x. Let's make a triangle here. Okay, more or less. Let's say this triangle has dimensions b as base and h as in height, right? And so we can divide this triangle into little strips, because now we know where is the location of the strips, the location of the center of gravity. So the strip that we are going to do is this strip here. The width of the strip is very little, is dx. This width is dx. The height of the strip is, let's call it y. So we know that the center of gravity of this strip, since it is very thin, this we can be considered horizontal here, and the center of gravity is right here in the middle. So the weight of this strip is here, but we are not calling this the weight anymore. We are calling it dA. And our expression is x bar is equal to integral of dA times x divided by a, right? So dA is equal to y times dx times x divided by a, right? So if we do this integral from 0 to b, we are sweeping all the strips that you can find from 0 to b in order to contemplate the whole area of the whole triangle, right? So the only thing that we need to do is to express y as a function of x in order to do the integral. So if we know that this triangle, the hypotenuse is part of this line. This line is a line that has an equation. This equation of a straight line mx plus b, right? With m is the slope. The slope of this line is h over b, and b is the intercept. Well, this b is not the same b as the base of the triangle. This is the intercept with the y-axis, right? Intercept. In this case, it's 0 because the line goes through the origin here. So our equation becomes y equals h over b times x. Okay? So then our expression here for the integral will be 0 to b. Y is h over b times x dx x divided by area. So here we have h over b can go out, and we have integral of 0 to b to x squared dx divided by area. So x bar is going to be equal to h over b times area for x cubed over 3 from 0 to b. So equals to h over b a b cubed over 3. So this becomes square. So we have h b squared over 3a. And we know the area of the triangle, right? The area of the triangle is 1/2 of b times h. So this becomes equals to 2/3 of b. That's it, 2/3 of b. This is x bar. This is, oh yeah. Okay, so we found that the location of a centroid of a triangle is at 2/3 of b. Let me put it here like a summary here. So we have our triangle. This distance is b. This distance is h. The center of gravity is somewhere here along this line, where this distance is 2/3 of b. How height here? What will be this height? Well, we can do the rotate this triangle 90 degrees, and do the same exercise, and then we will have the triangle like this. Now rotated 90 degrees, and here will be h, here will be b, and then we will find that we already have this location here at b over 3, and now we have this h over 3, if this is h. We don't have to repeat the whole process because it will be the same thing. So that's the location of the centroid of a triangle.
Professor, there's a question in the chat.
Yes, please. What is the question in the chat? Why was the I equals 2? Let me put that one here bigger. This point, the coordinates of that point, this is a general point of coordinates x, y. It's just any point on the line that defines the triangle. The line that defines the triangle is this line here, coordinates x, y. And the equation that relates x with y is this equation that for our specific triangle is this equation, but from x equals to 0 to x equals to b, right? And then I divided the triangle in tiny strips that are shown here on this red strip. This is the strip DA, right? This is clear. This strip has a width dx, and the dimensions of the strip is base times height. The base is dx and the height is y. dA is the area of the little strip that has base dx and y and height y. Is that understood already, or shall we? Okay. Let's do example 3. Hallelujah. You see it, right? Tell me that you see it.
Yes.
Whoa.
Yeah, we can see it.
Okay, so now I have to. Yes?
Yep.
All right. So a spandrel of a parabola is this area here between the parabola and the line and the x-axis. This is the element of the differential of area. This is the x, and this height is y. Why this height is y? Because those are the coordinates of this point. Every point in this line is the coordinates x, y. Yeah. Stop working every minute. X, y. These are the coordinates of every point on this line. And what relates to x with y is the equation of the parabola, kx squared. And if we define our parabola by this height and this base here, well, then then the equation, you can replace h and b because this point has coordinates bh. So that this equation has to be true also for that point. So when y is b, when y is h, x is b. So from here you can get k equals to h over b squared. So the equation of our parabola in this particular case is k, which is h over b squared times x squared. Our differential of area is equal to y times dx. So our equation of x bar is equal to integral from 0 to b of dA times x divided by area. So it was gonna be 1 over a integral from 0 to b of differential of area is y dx multiplied by x. And then we have 1 over a integral from 0 to b of y is this equation here. So it's gonna be h over b squared x squared, that's y. Then we have another x here and dx. So we have 1 over a integral from 0 to b of h over b squared. Well, this is a very silly step that I do here. Cube dx. So x bar equals to 1 over a h over b square x4 over 4 from 0 to b. So it's gonna be h over a b square times b 4 over 4. Did I miss anything? I hope not. Now we need to find a, right? We need a. We can find a as the integral of dA, right? So will be the integral from 0 to b of dA, and dA is again y dx. So the integral from 0 to b of y, which is h over b squared times x squared times bx. So the area is equal to h over b squared x cubed over 3 from 0 to b. So will be h over b squared b cubed over 3. So this would be, so it's hb over 3. So let's put this back into x bar. X bar would be equals to hb4 over a, which is, well, let's put this b square a4, and then the area is hb over 3. So I have here h goes with h. I have 2 b's and 3 b's with 4 b's, so just 1 b survives. So I have 3/4 of b. So this is the location of a centroid of a parabolic spandrel. What does that mean? Let me put it here. Our sector of parabola is like this, where this has dimension b here, this has dimension h here. The location is over here somewhere, and over here somewhere, and this distance is 3/4 of b. Therefore, this is 1/4 of b. So we cannot find at least the horizontal location of a parabolic spandrel where this point is the vertex of the parabola. So this equation of the centroid only works if you have the vertex of this parabola included as the corner of your spandrel. The spandrel is this area here. It's kind of like that area between the parabola and a vertical line here and the horizontal line here. All right. So we found so far we found the centroid of a little strip, the centroid of a rectangle, the centroid of a right triangle, the centroid of a sector of a parabola. So we have like four different figures from which we know the centroid because we calculated ourselves. We don't have to trust anybody. But we cannot find the centroids of every possible figure. So people have taken the time to do that, and you have to find tables with centroids of different figures. And there is some other figure that's very easy to think that the centroid of a circle is in the middle. The centroid of half a circle is not that easy. It's not it's somewhere here in a weird place. So for more figures, you can relate to a table where people have taken the time to find it. And now that you have the centroid of a bunch of figures, you can find the centroid of figures made of different or more basic figures that you can break your area into and find the centroid of more complex figures by dividing it in figures that you know the centroid. And then we will use this equation that centroid of a composed figure of different finite number of areas is equal to summation of each one of the areas multiplied by the corresponding centroid divided by the total area, right? And the same thing for the y equals summation of ai xi over a. For example, we have already the centroid of a triangle with a right angle here. With that one, we can find the centroid. How about the centroid of a triangle like this? So let's find the centroid of a triangle that is not right triangle. It's like this. So we can break it into two triangles which we know the location. So that, let's call it, will be example 4, I guess. Example 4. Let's say we have this triangle. Or let's say the base is here 12. This is 6, this is 6, and let's put something important here. 3. We could do this with letters, it's very general, but my point is to make the introduction of this table that you have to use when you do you break an area into a finite number of areas. So you divide the area into areas which you do know where the location of the centroid is. In this case will be this triangle, let's call it 1, and this 2. And you know what is the location of this triangle because we just found it. This distance is 1/3 of the base. This distance is 1/3 of the base. In this case, this distance will be 2, and this will be 2, right? 1/3 of the base. So when you want to do that, you have to make this table. Remember, a sub I, x sub I, y sub I, ai xi, ai yi, and you start filling the table. So 1, 2, a1 is equal to 1/2 of 6 times 3, so will be 9. The other triangle is also 9. The location of the centroid of the first triangle is here. The x will be 4. The x of the other triangle is from here to here. So it will be 6 plus 2, 8, right? And the height of the centroids are both the same. 1/3 of the total height. This total height is 3. 1/3 will be 1. So it will be 1 here and 1 here. And you do the multiplications. 9 times 4, 36. 9 times 8, 72. 9 times 1, 9. And 9 times 1, 9. And then you make the summation. Summation, all the areas here. Summation of areas, 9 plus 9, 18. Summation here, this is 108. Summation here, 18. So now x bar is equal to summation of fi xi over a. So will be 108 over 18 equals to 6. Y bar 18 over 18 equals 1. So our centroid, if this is 12 and this is 3, our is at 3 at 6 here right in the middle, and at 1 from height. So this is our centroid of this area. All right. Okay. I guess we are going right, but let's make one last example, because I want to introduce what happens if you have a hole in the figure. So you just basically subtract the hole. Let me make a little one last example here. I give
Professor,
you,
can you go up a little bit so I can see the last part that you were writing?
sorry, I was going too
Oh,
fast.
thank you.
Let me put it right there and I make the graph here for the last example. So I'm gonna make a figure here that is composed of a couple of triangles and a rectangle. Let's do this. Let's do this here. I'll go here. A little bit down. Let's go up here. And then go up like that. Supposed to be a triangle. Let's say this is 4.5. 4. Well, the figure is not very good at scale because of making this here like 3. And let's say that it has a hole here, right in the middle here. The radius of the circle is 1, and the center is 1.5. Okay, so we have this case. We break this into figures where you do know the center of gravity. That will be this triangle. Let's call this one 1. This square, this rectangle, let's call it 2. This other triangle 3, and the whole 4. So we do the table. Remember, a sub I, x sub I, y sub I, 8i xi, 8i yi. 1. The first triangle, area, 1/2 of 3 times 4.5, 6.75. The x of this triangle will be 2/3 of this distance, 2/3 of 4.5, that's 3. And the y coordinate of this will be 1/3 of 3, so that will be 1. Then area number 2 is just a rectangle, is 4 by 3, 12. The location of the centroid is 1/2 of 4, this is 2, 2 plus 4.5, 6.5. The y direction, 1/2 of 3, 1.5. Element 3 will be the other triangle. Area, this is area 1. Area 3, 1/2 of 4.5 times 3. So it would be 4.5 times 1.5. No.
Isn't it 6?
This is 6, right? 6, right? That's what we're getting at? 6. So it's
Times 4.5, isn't it?
yes. I screw up everything here. 3 times 4.5. 3 times 4.5. 13.5. 13.5. Then the location of the horizontal coordinate of the centroid, which is over here somewhere, is 1/3 of 4.5, which is 1.5 plus 8.5. What? 8.5, right? 8, what? X 10, right? 10. 4.5, 8.5, 9, 10. 10. And the height is 1/3 of 6, 2, 4. So when we included areas 1, 2, and 3, we include the whole area, including the hole. So now we need to put, so the hole in this, we are including the whole weight, like the hole has weight going down. So we need to remove that force of that weight going down by putting the weight of the hole, like if it was is pulling up instead of down. The way you do that is to put in that area negative here. The area of the circle is pi r squared, and the radius is 1, so it's minus pi, right? Minus pi. the location of the centroid is just the location of the centroid. So it's right here at 4 plus 4.5, 9.5, 9.5. And the height I said is 1.5. So now you do the multiplications. I have the multiplications here, so I'm gonna fill the table and you can check it later if you want. 6.75 times 3, 20.25. 6.75 times 1, 6.75. 12 times 6.5 is 78. 12 times 1.5 is 18. 13.5 times 10 is 135. And 13.5 times 2 is 27. And minus 3.14 times 9.5 is minus 26.7. And 3.14 times 1.5 is minus 4.71. So you just have to make the summations here, and you should get 29.11, 206.55, and 47.04. So X bar will be 206.55 divided by 29.11 equals 7.10, and Y bar will be 47.04 divided by, this is 29.11 equals to 1.61662. So to put it back here, will be something like 7.9. This is here is 4.5 plus 4 is 9.5. So 7 minus will be like over here, somewhere over here. And the height is 1.62, a little bit over 1.5. So this will be the center of gravity. Okay? Something very similar to what we did. You have one line like this and another line like this, and then you cut it here. So this distance, you know, let's call it D, and then you have here some coordinates. So you have here y1 and y2, and 1 of x and 2 times x, and then you will have to have this height here, let's call it h2, and all this height here h1, and then find the center of gravity of this triangle. Then you will have to set up element of differential area where this is dx, this is x, and this is let's call it h. So dA will be h times dx, which will be y1 minus y2 times dx. That will be the only change. The rest will be the same. You just have to find the equations. Basically, you have to find n1 and n2. Well, actually, very easy here. H1 over b, h2 over b, right? And you have your equations. And do the whole process, and you find the center of gravity, at least the x bar. You will find the x bar of this one here. Y bar will be a little different. That will be a nice exercise. Maybe that will be the question for the exam when it comes to the exam of the centroids.